we are going to host the recording onto the YouTube channel, so you can also access that later on. So this is the agenda for today. I'm going to do a very soft introduction, and then we're going to get into it. So first, we have a formal introduction of what CEINMS real-time is by Professor Massimo Sartori. Massimo is here on my right side. And after that, I'm going to give you an overview of our repository and the documentation that the team has put together. So I will show you where to access them and how you can find information. After that, Roger on my left is going to show us how you can set up CEINMS on your PC. So it's going to be for a certain operating system and for a certain template. It's not generic, but at least something for you to get started on CEINMS real time. After that, Salvatore across me has a really nice demonstrator plugged in where he's going to show the functionality of CEINMS, but also use two plugins. One that we already have that's publicly available, that's his plugin. And then he's also integrated his own plugin. Sorry, there's a bit of a technical issue on our end.
Yeah, but it's not affecting.
Oh, okay, cool. And then he has another plugin that he built himself from the templates that we have. So for reading from Accent's IMUs. So that's a nice demonstration where he shows the core of CEINMS, but also a plugin that we had within CEINMS, but also something that he built on top of that. After this, we expect the first part to be about an hour. After that, we are going to have you answer questions from the audience. What we would also like is if you have questions while we have the presentations, please put that in the chat. And then at a good point, we will take them one by one. So feel free to put your questions in the chat in the meantime. And in the open Q&A, we also have the opportunity for you to switch on your mic and maybe also speak up. But until then, you can also put your thoughts on the screen. I think that's the introduction that I have from my end. And I'm going to hand it over to Massimo, who's going to kick off the workshop.
All right, so I hope that you can all hear me, and I also hope that you can see my presentation. Just as a reminder, as you log in, make sure that your mic is off so that we don't have interferences. All right, so well, it's a pleasure to be here. Thanks all of you for showing up. I'd like to give a very brief introductions about what CEINMS real-time is and how it can be used. So it's a little bit of an introduction to dive into the topic. We have developed CEINMS real-time with the idea of essentially implementing three major steps. On one hand, to interface with, so to develop myoelectric interfaces with the human so that we can essentially measure bioelectrical signals from the body that are associated with movements, for example, EMG signals. But the main problem is that these bioelectrical signals, such as EMG signals, they don't explain human movements entirely, because movement is what underlies mechanical forces and accelerations. So these bioelectrical signals, such as EMGs, they actually need to be translated in the language of the musculoskeletal system. So we actually need an EMG-driven model that converts electrical information, electrical signals, into the resulting biomechanical forces that make us move. And that's the main reason why we developed CEINMS and CEINMS real-time, to implement these two-step neural interfaces or myoelectrical interfaces in the first step, and then secondly, to predict the resulting biomechanical forces happening inside of our body, such as muscle force or joint torque. And if you can do these two steps accurately, and if you can do them in real time, then essentially you have a way to interface wearable robots with the human body, such as exoskeletons or bionic limbs. And you have a very generalizable way to implement myoelectric control, volitional myoelectric control of wearable devices, as I will show in this presentation. So all of these three steps essentially can be done with CEINMS real-time, CEINMS-RT. So this is the outline of this presentation, I'd like to introduce what CEINMS-RT is. I'd like to provide a brief overview on how the CEINMS architecture works. And then I'd like to give you a few control examples on how we've been using this CEINMS real-time framework to implement robotic applications. So let's get started with the first one. So CEINMS real-time starts and stems from the CEINMS project. The CEINMS stands for Calibrated EMG-Informed Neuromusculoskeletal Modeling Tool. It's an offline tool that is available on cmtk.org. And essentially what CEINMS does is implementing a forward dynamic pipeline. So starting from estimates of muscle excitation, such as EMGs, we can simulate what's the resulting force produced in the muscle. And if we have representations of the musculoskeletal geometry, so if we know how muscle tendon units are arranged around bones, we can convert muscle forces into muscle moments. And then if you have a multi-body dynamic system, you can convert moments into accelerations, and then you can integrate accelerations forward, and you can get velocity and positions. So what we do is essentially CEINMS works by measuring EMGs and processing EMGs directly within the CEINMS pipeline. And then we use frameworks such as OpenSIMOS or MyoSuite to essentially define musculoskeletal geometry. So we use MyoSuite or OpenSIM to essentially estimate moment arms and muscle tendon length. We call this muscle tendon kinematics. So these are the two major inputs of CEINMS, essentially EMGs and then muscle tendon kinematics information. So basically muscle tendon lengths and moment arms. CEINMS takes this input data and essentially estimates the mechanics of muscle tendon units, essentially estimate how muscle activations generate muscle force, how muscle forces engage with elastic tendons, and how multiple muscles project their force onto the joint. And if you have a good estimates of muscle tendon force and joint and the resulting joint moments, then you can use these estimates to control digital twins in real time, or even to control physical devices such as prostheses or exoskeletons. So the CEINMS project is a long-standing project that initiated many years ago, and it's been contributed by many universities and many collaborators that I would like to acknowledge with this slide. Over the years, we developed open loop and closed loop pipelines. CEINMS is a completely generalizable framework, so you can apply it to simulate any musculoskeletal model, upper limb model, lower limb model, or trunk model. The code is very modular, so you don't need to change anything in the code. You just need to upload a new geometry, and this will be handled immediately. And again, so basically CEINMS, the offline version is available on cmtk.org. The offline versions of CEINMS has been used widely around the world, and we are starting to also have independent research started to demonstrate that this toolbox is represent currently one of the best ways for calculating internal forces. And if we see on PubMed the use of CEINMS and EMG-driven models of the years, we can see that there's a positive trend in the way that these techniques are being used. And this motivated us to bring the CEINMS project one step forward and to make it real time, so that the community could use it for real time and robotic applications. So this essentially brings us to the CEINMS real time framework. Before I go to CEINMS real time, I'd like to emphasize that over the years we validated the code that we provided open source in multiple ways. So we validated it at the level of joint moments. So we have several studies showing that we can estimate joint moments accurately across a range of movements. We validated it against internal compressive forces with a specific set of subjects who were implanted with an instrumented endoprosthesis. So these subjects that had total knee replacement, and the endoprosthesis that was instrumented, that was integrated in the knee, had a force transducers, and so we could directly validate CEINMS capabilities at estimating compressive knee forces with a reference sensor. And more recently, we validated the ability of CEINMS in estimating joint stiffness during dynamic movement. So we have pretty good confidence that the musculoskeletal forces that we simulate with this framework are quite realistic. So now we recently made this toolbox essentially operating in real time. So the code has been optimized to work in real time. It's pretty fast. And we made this toolbox available, which is available on GitHub, and Irfan later on will give a little bit of an overview of the GitHub website. We also have a documentation that already provides information on how to install and how to compile the code, as well as there are some tutorials that guide you through the use of lower limb and upper limb models. And again, before I move forward, I'd like to stress that the real-time versions of CEINMS-RT has been pushed forward by a multi-century collaboration between University of Twente in the Netherlands, McGill University in Canada, and Griffith University in Australia. And these are the major people that have so far. All right, I'd like to give a little bit of an overview of how CEINMS works. This is a structure of the major components of CEINMS. So the shaded line, the shaded area here represents the CEINMS infrastructure. Essentially, CEINMS communicates with the external world using what we call TCP/IP socket. And in the CEINMS terminology, we call them plugins. So you will hear the word plugin several times in this webinar. So plugins, they are essentially TCP/IP sockets that are open, and they listen to data coming in from external devices. So you can have, for example, a plugin that communicates with an EMG amplifier. For example, we have a Delsys plugin that can communicate with Delsys EMG systems. And so this plugin listens for EMG data coming into TCP/IP or into a UDP port. But you can also have a plugin that listens to data coming in from a motion capture system, right? So the EMG provides EMG information, and the motion capture system provides joint angles. And the plugins, they essentially feed EMG and joint angles data to the core of CEINMS, which is represented by a musculoskeletal model and by a spline module. What the spline module does is essentially converting joint angles into estimates of muscle tendon lengths and muscle moment arms. So these splines, they essentially synthesize the musculoskeletal geometry that's being used in the simulation. So if you are loading a trunk model, or if you're loading a leg model, or if you're loading an arm model, these spline methods, they are this spline block is essentially a family of splines that model every single muscle tendon unit as a multi-variable function that, given input joint angles, estimates what are the resulting muscle tendon moment arms and muscle tendon lengths. And then through the EMG plugin, we essentially get muscle activations, which we feed into the musculoskeletal model. And the musculoskeletal model uses activation, moment arms, and muscle tendon lengths to essentially estimate the resulting muscle forces and joint moments. And these are displayed to the user in real time through a graphical user interface, a simple graphical user interface. So in this table here, you can see the existing plugins, which are available open source. So we already have plugins to communicate with CEINMS, which is a very common inertial measurement unit system. We have plugins to communicate with ROS. So if you want to run CEINMS on ROS, we already have a plugin for that. We have a plugin for DELSYS, as I showed. We have a plugin for OpenSIM-RT or SIM. If you want to stream real-time OpenSIM variables to CEINMS, that can be done. We have a plugin for TwinCat if you want to use a hard real-time communication protocol, and so forth. So these are essentially some plugins that are already available, which we think will serve some of the community needs. And again, yeah, basically, CEINMS is currently able to estimate moments, compressive loads, and stiffness in real time. And again, this is the core of CEINMS, essentially. All right, let's go a little bit on the control and communication framework. I'd like to show a little bit essentially how this infrastructure can be used to implement control applications. And the idea is very simple. The idea is to measure EMG signals from target muscles. And through CEINMS, you can again estimate how these EMG signals they essentially dictate the behavior of the musculoskeletal system. So you can essentially predict what are the resulting musculoskeletal forces. And then these forces can be used to essentially implement proportional myoelectric controllers for exoskeletons. So this is typically the typical control paradigm that we have been using in the past. You will see that again here we have the same two inputs that I showed in the previous slide. So we have EMG signals and joint angles, which are the sensors that we typically measure from the subject. So if you have a subject walking, we measure EMGs and joint angles. These EMGs and joint angles, they go into the CEINMS framework, which is essentially the same framework that I showed you before, where we have the spline methods that essentially takes joint angles and converts them into moment arms and muscle tendon length. And then we have muscle activations that go into a muscle model, which then predicts muscle tendon force. And muscle tendon force is then multiplied with moment arms to predict, in this case, joint moments. And then, so in this way, we predict the biological joint moments in a target joint, in this case, in the ankle joint. And these biological joint moments, they now become the reference torque for the low-level controller, in this case of an ankle exoskeleton. So this CEINMS estimated joint moments, they become the reference torque that needs to be tracked by the ankle exoskeleton in order to assist the subject, in this case, during walking trials. So what you see here is essentially two control layers. CEINMS real-time operates as a high-level or a middle-level controller, which essentially interpret EMGs and joint angles with respect to the resulting joint moments. And then you have a low-level controller that essentially tracks reference joint moments provided by CEINMS. Now, this low-level controller is a fancy controller that has several components. He has a disturbance observer. He has a feed-forward model to increase the bandwidth. But essentially, what this is essentially a simple tracking controller, which essentially takes CEINMS estimated joint torques. This joint torque is multiplied by a support ratio, which basically tells which percentage of the biological torque needs to be tracked by the exoskeleton. So if the support ratio is 0.4, only 40% of the biological torque needs to be tracked. And this support ratio is essentially used to essentially implement a simple PD or PID controller. Basically, this scaled biological torque becomes the target torque. And then the error essentially between the current torque exerted by the exoskeleton and the target torque is used to implement a feedback controller. And so this simple control schemes allows you to implement myoelectric proportional torque control in a variety of devices. So you can essentially control bilateral ankle exoskeletons in real time. So as the subject walks, we can estimate the biological torque at the ankle joint in real time. This is essentially the blue signal. And as I showed you before, the blue signal can now be downscaled by a support ratio. In this case, we have support ratios of 0.4 to generate the orange torque. And the orange torque is the torque that the exoskeleton is now tracking. So what you have now is a sort of shared control paradigm where the exoskeleton provides a percentage of the total torque needed to walk, and the human provides the rest. So in this case, you are augmenting the capability of walking. And we have shown that this paradigm is quite versatile because the subject can walk across different speeds and across different ground elevation. And the exoskeleton is always able to provide a biomechanical benefit. So it's always able to essentially enable the subject walking at given speeds and given elevations using less torque with respect to the condition where the exoskeleton is off. So this was promising. And I like to end this presentation showing a little bit of control examples of how this paradigm was used in a variety of control applications that may or may not resonate with you. So we've used CEINMS not only with ankle exoskeletons, but also with trunk exoskeletons. So we are able to simulate in real time the mechanics of large-scale models. So in this case, we use CEINMS to simulate trunk models that included about 240 muscle tendon units in real time. And we use these models to estimate in real time the joint torques and the compressive loads acting on the lumbar joint, which is due to about 240 muscle tendon units real time. These histograms, they actually show the distribution of the time delay of different CEINMS blocks. So you can see that the spline module, the module that converts joint angles into muscle tendon kinematics, on average runs on 0.40 milliseconds. Whereas the core CEINMS module on average runs on 0.31 milliseconds. So we are actually able to run the entire pipeline in about 30, 34 milliseconds, 35 milliseconds, which means that we are pretty much below the electromechanical delay of the muscle, which means that we can actually estimate muscle force or joint torque before that force or that torque actually happens in the body. So we actually have a prediction horizon advantage with respect to the body. And we use this real-time trunk model in this study to control a trunk exoskeleton. This is a simple exosuit that is actuated by batten cables, and these batten cables are connected to linear stages. And so as the subject performs lifting tasks, we have a real-time biomechanical model that essentially estimates lumbar moments and engages the exoskeleton. And this slide is to show that CEINMS real-time can be used not only to control robots that are connected in parallel with the human body, such as exoskeletons, but it can also be used to control robots that are connected in series with the body, such as prostheses. And the idea is pretty much the same. You will measure EMG signals from the remaining muscles, the muscles remaining in the residual leg after the amputation. These EMG signals, they are fed into a CEINMS model of the phantom limb, the limb that's missing, the limb that's been removed due to the amputation. And in this way, you can use CEINMS to estimate what are the joint torques exerted in the phantom joint as the subject is moving the phantom joint. And then you can essentially feed these torques back to the prosthesis so that the prosthesis renders the mechanics of the phantom limb in the real world. And again, if the joint torques estimates of the phantom limb are accurate, then the behavior of the prosthesis will be perceived as very natural. And we recently implemented these ideas on transtibial amputees. And this is a video showing how these amputees can walk and they can control in a fully volitional way, essentially a robotic ankle device. So there's no state machine implemented here. There are no predefined rules. The subject is in control of the prosthesis at all times. And what he's essentially doing, he's essentially thinking of flexing and extending the frontal limb. And the resulting EMG signals, they are converted into torques, which are then fed into the prosthesis. This is an example of the torque of the plantar dorsiflexion torque that's been predicted from this walking trial, which is then controlling the prosthesis in real time. So it's a very versatile way of controlling. Similar ideas, we also apply them on upper limb prosthesis. And this is the last use case, and it's a use case that's coming from Griffith University, which is one of the three co-developers teams of CEINMS Real Time. And what they did is really cool because they use CEINMS Real Time in the context of spinal cord injuries. And essentially they have a neurorobotic system that involves an arm, a stationary arm exoskeleton, so the Armeo Power exoskeleton. But they also use a muscle stimulator to implement functional electrical stimulations of arm muscles. And they essentially use the CEINMS framework in real time to control both the exoskeleton and the functional electrical stimulator. And again, the structure is very similar to what I showed you before. This is the core CEINMS pipeline, which essentially takes raw EMGs, joint angles directly from the exoskeleton. But in this case, they're using CEINMS to not only to fine-tune the torque of the exo, but also to fine-tune the functional electrical stimulation given to the muscles. And what they found is that using these CEINMS-controlled neurorobotic platforms, they actually found that they were able to have the subjects performing arm tasks by exerting larger forces in their muscles and larger moments with respect to the platform that did not use this hybrid control of the exoskeleton and the functional electrical stimulation. So these are very promising results. So again, this is just a summary of how you can use CEINMS to really control in a very generalizable way robots such as arm exosuits, arm prostheses, lower limb exoskeletons, lower limb prostheses, and trunk exoskeletons. So it's a very generalizable human-machine interface that we made open source, and we hope that will be useful for you guys. This is my last slide. This is again the QR code that essentially directs you towards the GitHub. And this is a little bit of a very brief guideline of what's coming next. There's going to be a new release coming out soon. We call it version 1.2.1. This version is going to fix a few issues that we found with the spline block that I showed you before, which essentially converts joint angles into muscle tendon length and open arms. There are some small bugs that need to be fixed there. And this release is also going to provide some code optimization to make the code more optimized. Then we are expecting release 1.3 in the beginning of 2026, which will include a Linux release of CEINMS. So we will have a Linux installations of CEINMS. So at that level, we will be able to support both Windows and Linux. And what's interesting is that we want to provide what we call one script installation. So there will be a single installation script that will handle all the dependencies and all the installations, starting from one single script that you will just have to run from your computer. So it will be a pretty streamlined way of installing CEINMS on Linux and Windows. And then we will have release 1.4 that's coming in the second half of 2026, where we will release the ability of estimate joint stiffness in real time which I think can be useful for a variety of applications. Okay, that's it from my side. I think we can move on with the rest of the presentations.
Cool. I think what we could do now is maybe take a couple of questions. There are already two on the chat. I don't know if you can see them, or should I read it out?
Yes.
So the first one from Sachin. I think his question is about the latencies, but then I think that's also covered in the slides. But I think the main part is how does it affect the control accuracy or validation when interfaced with the robot or digital environment?
Yeah. See, so indeed, the latency is, maybe I can then share back my screen so that I can navigate to the actual slides in a second. Fantastic. Okay, yeah, indeed. So the latency, this is a study that we released in 2023. The latency is pretty low. So the EMG-driven model itself is running in on average on 0.31 milli. So every frame of estimated torque comes out with a latency of 0.31 milliseconds, and the spline about 0.39. This is the histogram of OpenSIM. So that's how much it takes to do inverse kinematics in OpenSIM. But the idea is that we are able to operate below about 34 milliseconds in total. But we could be potentially faster depending on the computer that you use. So in this case, we used a normal laptop. We are now running CEINMS real-time on Raspberry Pis, which are not very powerful. But you can also run CEINMS on NVIDIA hardware, which makes it even faster, especially if you have many muscles, such as a trunk model. You can actually parallelize the computations of many muscles. And so going back to the control, you want to be you want to have your CEINMS pipeline operating around the electrical mechanical delay, because if you start to have delays in the order of 300 milliseconds, then the subject will perceive a latency with respect, between the intended movement that they're doing and the movement of the robot. So this delay starts to become apparent when the latency is around 300 milliseconds. But with our numbers, we are far below this, because we are around 30 milliseconds of real-time application with a normal laptop that was not very powerful. So I don't expect issues in this case.
Yeah. Cool. Maybe one more question, and then we could continue, and then we get back to questions in the Q&A. I think we could take the question from Utku, where he talks about access to real time. So I don't know if you can see the question in the chat. I can also share it on the screen.
Look perfect. It's exciting. The system looks a bit.
So the one above. So on the slides, part 4, adaptive wearable robots. The high-level controller executes in real time. If so, is the high-level controller hard real time or soft real time? What kind of operating system runs the high-level controller?
Okay, cool. Yeah, so then we're going to this part here, I think. In this part here, I guess. Yeah. Yeah, so in this specific study, and in all the studies that actually show, so the ankle exoskeleton, the trunk exoskeleton, and the ankle prosthesis, we use EtherCAT, which is a hard real-time communication protocol to control robotic devices in a hard real-time manner. So we have hard real-time deadlines. But this is only happening at the low-level stage. The middle-level stage is a soft real-time, because CEINMS essentially communicates with EtherCAT through plugins, and the plugins, they work using UDP or TCP/IP. So the middle level, the CEINMS layer, actually sends data packages through a UDP, which means that there will be a variable latency at that stage. But the low-level controller, which runs on EtherCAT, makes sure that reference torque commands are sent to the low-level controller with fixed clocks. irrespectively of how updated the torque coming from CEINMS is. So there can be some not fully. So it could be that the low-level controller will run faster than the high-level controller. So it will send basically similar values of torque in some time frames. But this doesn't matter because the low-level controller is running at way higher frequencies with respect to the low-level controller. So the low-level controller runs at about 1 kilohertz, whereas the middle-level controller typically runs to 50 to 100 hertz. So it's normal to have this difference.
Cool. All right, then I think what I would like to do is move on to the next part and then come back to the questions towards the end, if that's all right. Okay, so what I would like to do for the next session is just give you an overview of the environment that we have in CEINMS. Screen first. All right, so you should be able to see my screen now. Right, so what do we have with CEINMS? This is kind of our landing page at GitHub, right? So we host all our repositories here at the CEINMS real-time projects. And for easy access, we have the 3 pinned repos. We have CEINMS real-time core CPP. So this is predominantly in C++, our core of CEINMS real-time. We also have a link to read the docs, which gives you the documentation of how to sort of set up CEINMS and the different plugins that are associated with it. And then we also have another repo, which is at the moment the way that we suggest how you install CEINMS real-time. But as Massimo mentioned, as one of our next steps in the timeline is to have a much easier way to set up CEINMS, because right now this approach that we provide requires you to install each of the dependencies separately, whereas the other ones is a bit more, the other approach that we want to have will be a bit more efficient and faster. So what do we have within the main sort of the landing page with the CEINMS project are also other repositories for different plugins. So you can also access different plugins in the repository. But what is easiest is to just go to read the docs. So when we go to read the docs, we have access to the link, which summarizes the project and all the other things that you could do around it. On the left, we have the introduction, which gives you a very brief overview of CEINMS real-time, what it is and how it's set up. Then we ask you to take a look at the installation. So this installation is based on the repository that we showed before, where we have a script installed CEINMS.ps1 that installs all the required dependencies. I can quickly show you how that looks like. So in the CEINMS real-time installer repo, we have the different executables for different dependencies. And when you run our post script here, that installs each of them and also ensures that it's placed in the right location on your OS. Coming back to the documentation, here you can read a little bit about how to set up CEINMS and how to install it. After this part, Roger is going to show us how to do that very briefly on a say a fresh PC. How can you get started with CEINMS on Windows? And then you can also find support for how to compile it. And we use CMake to sort of compile CEINMS, build the different projects, and also the plugins that you want. Here we summarize in repositories all the different additional repos that we have within CEINMS. So you can see here in the repositories, we have the core, but also different plugins. So as we mentioned in the previous presentation, the different plugins that already exists include Delsys, Morticon, UDP plugins, and so on. So different existing commercially available devices, but also communication plugins that allow you to open a port where CEINMS can listen to inputs from, say, the outside. We also provide with you 3 models for you to start testing. We have the back model. The back model focuses on the lumbocircle joints, and the idea is to model the moments and the compressive loads around the lumbosacral joint, and also the muscle forces of all the muscles that drive this joint. And this is quite a large model that we test with for back exoskeletons. Then we have the lower limb model, which is kind of our suggestion for you to get started off with. So this model includes the ankle, the knee, and also the hip for gait. So for somebody starting off with CEINMS, we recommend starting off with a simple lower limb model that focuses on the ankle, so you know how different model parameters affect your calibration or execution. And then we also have the upper limb model, and here we look at the shoulder. So we can probably jump into the models itself to see what is provided with it. Sorry. So in the tutorial, we have the different models also explained. So in the lower limb model, we also provide the GitHub repo and how you can set up the different models. CEINMS has two parts, and also one of the questions that one of you asked is there's the execution part, which is running CEINMS in real time, right? So this is when you have a model that has already been personalized and calibrated. Then you can use CEINMS to run the core after it communicates with the inputs for EMG or joint angles. And then it provides the torques or the compressive loads or stiffness, depending on what you want. And here in this page, you can also see the modifiers that you can have along with CEINMS. So CEINMS requires that you run the command CEINMS.exe, which is placed in your bin-win debug folder path. And along with that, you have several modifiers that you could use. There are two modifiers that you need to include, which is the E, which is your execution string, and your S, which is your subject XML. So these two are needed for your CEINMS because one of them defines how CEINMS is going to be executed, what are the plugins that it's talking to, and the S is the subject model that you use to run CEINMS. In addition to that, you also have other modifiers. For instance, if you use P, then you can sort of process data from a folder that already has data that is pre-recorded. So you could also run CEINMS real-time offline to do some testing. You have -G, which is to switch on the GUI. So if you don't include -G, then the GUI by default does not pop up. You have -R, which what it does, after it executes, CEINMS saves the file that it generates. So this includes the torques, the muscle kinematics, which includes the fiber length, the fiber velocity, the tendon, muscle tendon length, and so on. And then you also have a -E and -V, which is the level of information that you get while running CEINMS. -E and -S, which I already mentioned. These are required tags. And then additionally, you also have -T, which is, for instance, if you have CEINMS that takes too much time, or for instance, you want to stop CEINMS after it executes for a given amount of time, then you could use this. One use case is if you want CEINMS to stop calibration after a few hours, then you can also set it if you would like. And then you have these additional tags. So these are the tags that you have for the execution. So CEINMS has two ways that you can be used. One is execution, where you run the model, so you run the forward dynamics, but then you also have the calibration mode, which you can see in the tutorial, where in addition to just running CEINMS all the way to the end, you also have a calibrate option. And what the calibrate option does, it takes a subject model that you have predefined, and it adjusts the muscle parameters. It adjusts the maximum isometric force of each muscle, the tendon slack length, the optimal fiber length, and also something to do with the activation dynamics. It changes these, or it optimizes this to make the model more personalized. So this is the second way that you could use CEINMS. So coming back to a brief summary, in CEINMS, we have a list of repositories. We have the core that contains the core muscle model, which is usually run in forward dynamics when you execute CEINMS. We also provide these plugins. These are currently available and free to use, and we are building more plugins in the coming years. Also what was mentioned in the previous presentation. We have 3 models for you to get started with, example models. And if you're starting off really from scratch, our suggestion is to start with the lower limb model, especially focusing on the ankle degree of freedom. And if you are also willing to create a plugin for yourself, we also provide templates for plugins, right? So here we have three different templates. For instance, the EMG and angle plugin is giving you an example of how you can read EMG or angle and provide it to Xsense. And then you also have plugins that show how you could not only read information from outside to CEINMS, but also provide something that you want. So at the moment, we provide torques or compressive loads, but you could also add additional muscle parameters if you want. For instance, if you're interested in the force of a specific muscle, you could also write a plugin to send that out if you would like. So this is what we have within CEINMS. We suggest you to take a look at the read the docs to understand that. And if you have some issues setting up CEINMS, we also refer you to the CEINMS core repository, and we have a issues page. This is constantly monitored by the CEINMS team, but also we ask you as a community to sort of help each other out. If you have issues with CEINMS, please open that here. This is the fastest way that you could get your questions resolved. Please take a look at the existing issues so that you don't ask the same question twice, and also ensure that you use best practices when you're asking your questions. So ensure that you state clearly what your, for instance, your OS is, what have you tried, some screenshots, so that we can also reproduce and help you better. This is our environment. In addition to that, we also have a discussions page, and this is for you to come up with ideas of what you would like to do with CEINMS. What we really want CEINMS to be is a community endeavor, so we want your inputs to sort of make it more than what we initially planned it out to be. If you have ideas of what you could add, and here I give a very an attempted example of what could be added to CEINMS, for instance, modeling fatigue in real time, but you could also come up with other ideas. And this is for the community to come up with ideas, but also to come up with plugins that could sort of solve it. So it's not just coming up with new ideas, but also with solutions for CEINMS. So that's very briefly the CEINMS environment in GitHub and the read the docs. I'm now going to hand over to Roger, who's going to do a brief demonstration of how to set it up on a PC.
Okay. Well, welcome everyone. I will share my screen. So as mentioned, we are using two repositories, one for the core of CEINMS and one for the installation of CEINMS. Like was told, this will change. So with the release of 1.3, we will get rid of this complete repository, and the install scripts will be part of the core of CEINMS. So to install, you have to clone this repository. So I want to stress this out because some people try to download this source, but because of a bug in GitHub, that doesn't work. All the executables are becoming corrupt. So you have to clone this repository in order for the installation to work. I already cloned this, and we need to, like it states in the README, we need to start PowerShell in administrative mode. I also set the execution policy for scripts. And then it's a question of running this PowerShell script. And for the sake of this demo, I skip some installations. But it's just about entering and doing its stuff. Maybe while it's running, I can mention some problems that you guys stumbled into. So, as was mentioned, we're using CMake to do the build of the core of CEINMS. And what CMake does, it's searching for components like OpenSim or other dependencies in order to compile. And that can give some conflicts. For instance, when you have a existing release or installation of OpenSim on your system, that can conflict with the OpenSim dependency of CEINMS. So it's imperative that you change the reference to OpenSim. I can show you that later. But that is that can sometimes be an issue, and we will try to fix that in the new coming script that we will force CMake to look for the specific installations of the dependencies that install script is using. So, for instance, with the OpenSIM, when you install OpenSIM, the release configuration is most likely installed. So I don't know if you know, but when you compile a C++ project, you can choose different configurations like debug or release, and when you download OpenSIM from the internet, mostly the release configuration is installed. But at default, CEINMS is running in debug configuration. Because we like to run debug enabled. So that can conflict. So that's something you have to need to be careful about. And also, when you install OpenSIM or other dependency yourself from the internet, most likely it can be that your path, your search path in Windows is modified, and the OpenSIM version that you install is found first before the path of the OpenSIM that we need for CEINMS. So that could also give a conflict. Yeah, and it's not really that exciting, but this is the setup that is done. And yeah, we were gonna use we're gonna go to one script that will download and install everything. So we will get rid of this large repository, and that will hopefully help you to get to install CEINMS without any issues. Yeah, that's about it. What I can show you about installing CEINMS. Maybe when there are questions about install or issues, and I can answer that now, or otherwise you can insert the issue at the portal like Irfan showed. So that's my. Oh, yeah.
Thanks, Roger. All right, so should we take questions or move to the demo?
Let's see if there are some additional questions. I think what, yeah, basically what Roger showed is a viable script that can be used to run the installation. Please try it, and if you have issues, use the issue tracker to flag it so that we can address it. Yeah, if there are no additional questions, then I suggest that we move on with the demo. We would like to give a live demo on how CEINMS real-time can be used in real time to process EMG and IMU data and simulate an ARM model. So Salvatore that will provide this demo.
So, hello everyone. My name is Salvatore Li Gioi, and I am a PhD student at Campus Biomedico of University of Rome at Lab, and nowadays I'm doing my visiting period on robotics lab in University of Twente. So today I'm going to show you a real-time demonstration of CEINMS by using external device to fed in input to CEINMS, which are the Xsense IMU, but also the CCMG sensors. So briefly, what I want to show you is how to fed EMG signals and kinematics in CEINMS in order to estimate some biomechanical parameters, which are mass or tendon unit force, but also joint dynamics. So in order to do so, what we have to do briefly is to talk about, I'm going to talk about firstly how to use the DERSYS, how to set up CEINMS with the DERSYS CMG. So this is the block scheme of what you should do if you want to create a communication with the DERSYS software and CEINMS. So first of all, what you have to do is to establish a communication with the Trino base control. In order to do that, what you have to do is to install the Trino control SDK. So I'm going to show you in this link. So in particular, you can install the Trino SDK. The Trino SDK by installing OMGWorks, or if you want to install only the SDK, you can use this one. So you have two ways to install the Trino SDK, and it is necessary if you want to if you want that your PC communicate with the Trino SDK. Then also there is a Python script which communicates with the DERSYS Trino by using the TCP protocol. And in particular, this Python I'm tested all in Python 3.9. And if you want to communicate with, if you want to read MG data, there is an open source GitHub library that is called PyTrino. And in particular, this library allows you to communicate with the Trino base station by using the SDK that I showed you before. And just let you know that in these scripts, also in every time you have to filtering and normalize the data. Then the script goes send these all the MG that they are using to CEINMS, and in particular, in order to have a communication with a UDP protocol with CEINMS and Python, what you have to do is to use an EMG UDP plugin that is available in the open source repository. So what we have to do is to clone this plugin, and then by using the documentation that's here mentioned, what you have to do is to follow the step in order to install the plugin. So after that, this plugin has the aim to create a UDP socket that allows to CEINMS to receive EMG data. And when we have EMG data, CEINMS is able to estimate our biomechanical parameters. Moreover, the same similar stuff you have to do if you want to create a communication with FIMU, XSense, and CEINMS. So first of all, you always have to install the SDK. And in particular, to install the SDK, I provide you this link. And what you have to do is to install this software, which is provide the SDK and so the driver to communicate with a Windows base station. Once that, there is another Python script which is able to read the MU data by using this Python library that you have to install in Python 3.9, and this is provided in the SDK. And also the script, what also do is to estimate, in this case, the elbow angle. After that, what you have to do is to, at the same time, also create another socket that allows to CEINMS to receive angle data. So this plugin is not public yet, but we aim to public it as soon as possible. And it means the same things, the EMG UDP socket. So with the EMG UDP socket, you are able to receive EMG data. In this case, you are able to receive elbow data or other data, joint data. And then this data go inside to CEINMS. So this is in particular all as a brief summary of what this demo is going to work. In particular, we have IMG Python script that is able, thanks to the SDK of the Trino, to read, filter, and normalize IMG data. We have the IMU Python script that is able to read the IMU data and also extract the angles. And we have that all of these parameters go inside to CEINMS, which allow us to estimate the muscle force and the joint dynamics. What I want to mention is that first we are going to launch CEINMS, and then we are going to launch the AMU and the MG scripts that allow us to estimate the parameters.
Right.
So, yeah. Yeah. So what you have to do is to maybe the button.
Yeah.
What you are going to do is then to set up to put the AMUs. Okay. Okay, we put the AMUs. Then we have to put the MG. So in order to communicate with the MG, what you have to do is to open the Trinium control utility software that is installed by install the SDK. And by doing that, you're gonna see that at this moment, the system is not communicate with any sensor because we have to turn on the sensor. In particular, we are gonna use two sensors. So the first one will be used for the biceps, and the third one for the triceps. In order to do so, you have also to turn on the sensor, and then what you can see is that when you turn on the sensor, the system is able to show you that which sensor is turned on. Then what you have to do is to touch the sensor. Okay. So what you should have to do is at the same time, before to attach the sensor, is to briefly clean the skin. And for this, so this is for the biceps, and this one is for the triceps. And then what you have to do first one is to launch CEINMS. So in particular, we're gonna open this one. And as you can see, this is how to launch CEINMS. In particular, we launched the executable. And with this one, and also we have also Irfan told you the execution file, and also the model that we are going to use, and there is -G in order to have the GUI. Yes, so the executable file is here.
No, not this one. Execution-RT.
Oh, yes. Yeah, so okay, so this is the execution-RT, in which also in CEINMS what you can do is to design the type of tendon that you want to use, and at the same time you have to talk to CEINMS what UDP you want to use. So in this case, we are going to use the MG UDP Simulink, and you have to tell the DDL file, and also the execution EMG XML, which talk to CEINMS which muscle we are going to use, and at the same time which sensor we are going to feed the muscle. So if you want, I'm going to show you here. Sorry. So in particular, we have we set the UDP port, and if you want to choose the type, which muscle, sorry, I took the wrong one. Okay.
So this is the subject XML, right?
Yeah, this is the subject XML, and if you go down, what you're able to do is, in this case, we are going to use only two muscle. And what you can do in this file is also to assign which EMG information goes in which muscle. So we have that EMG1 goes with the bicep short, and EMG2 goes to tricep med. So after that, so we can launch CEINMS. And at the moment, CEINMS is not now receiving no data. So what we have to do is to launch the other two scripts. So DMG scripts. So just open and then launch the script.
So this is a script that you've written, which calls, which connects with the EMG SDK,
Yes.
and also sends that data on.
Since that these scripts do two stuff. So in particular, in three stuff. So one is read data, one filtering data, and then using the UDP protocol to send data to CEINMS.
And the same thing for IMU.
Yes.
Also does three things.
Yeah.
So it reads from the two IMUs on my hand, and then estimates the angle between the two IMUs, and then opens a UDP port to send to.
Okay.
Yeah.
Here we have a real-time demonstration of CEINMS.
So you can see with my arm moving, the model also moves. So this is kinematics only that you're seeing right now. And on the left, you have the muscle force.
Yeah, we have also biceps.
So these are the EMGs. So
Yeah.
if I squeeze my biceps,
Yeah.
and then if you, you can also show the tricep.
Yeah.
Right, so if I activate my triceps, so there's a bit of a normalization that we need to adjust, but otherwise you can see that it's, when I squeeze my bicep, the bicep goes up. When I squeeze my tricep, the reverse happens.
And you cannot show this one. So this one by.
So this is the torque. Yeah.
Yeah.
So if I'm staying still, and then if I go, this is flexion, and this is extension. So you can see how this is a very simple model, and what it's trying to do is it has the kinematics, which gives you the force in the passive range, but also the activation of the muscle that you see here, which also gives you the scaling of the force, and therefore you get the net torque, which is a sum of the forces times the moment arms around the elbow joints. Then you get the forces that is needed to sort of lift anything that I have on my hands. And that's the CEINMS GUI that you're seeing right now. By default, you can have the muscle force. So the muscle force of all the muscles. So right now we just have two muscles, but then depending on your model, you can see all the muscles that you define, and you can see the activation of all the EMGs that you have. You can also use EMGs to drive more than one muscle. For instance, in the OpenSim, you have 3 triceps muscles, long, lat, and med. So you could use the same muscle EMG to drive them. And then eventually you can also define the degree of freedom. And in this work, what Salvatore has done is looking at the elbow flexion, and that's the degree of freedom that he's defined. I think these are additional things that you could add for your workflow. This is additional graphs that you can add depending on what you want to save, and that's something that you can customize if you want to see more than the muscle force, EMG, and the torques. If you go back to your presentation.
Yes.
And go to the last slide. Right, so what we showed now is that the EMG Python script is something that is already available, and the CEINMS real-time is, of course, the core that we have. But what Salvatore did was he built his own plugin, the IMU Python script, which was not available. So that's something that he could do based on the templates and based on the existing framework, and then have a simple demo for his use case. Yeah. Anything else to add, you guys? Massimo and Sartori?
No, maybe, I mean, this is just to show that you can run the whole pipeline that I showed in the presentation essentially in real time. So again, the John angles coming from the IMUs, they go into a real-time spline block that estimates muscle tendon, moment arms, and muscle tendon length, which are not displayed in the GUI right now. And then EMGs and muscle tendon lengths are used to estimate muscle force, which are the 2 histograms at the top. In this case, just for 2 simple muscles, 2 antagonists, monoarticular muscles, the biceps and the triceps, and everything goes to torque. And then in principle, you can use that tool to control, devices. But this is just one way of doing it. There are different ways of doing it. Yeah, it's a simple demo on how to do that. Another thing, before Salvatore showed a few configuration files. And you can, there's another interesting resource that's available. So there are two resources that are very interesting for you to understand how the configuration files work. One is the CEINMS-RT paper that is currently on Tech Archive. The paper is actually linked from the GitHub website. So if you go there, you can go to the paper, and the paper gives you an introductions about the configuration files. And then you can also use the documentations of CEINMS offline, which is on syndicated.org, which also gives a lot of information about how the configuration files work and how they should be set up.
Cool. I think, thanks a lot, Salvatore, for the demo. Then I think the floor is for you, the people in the audience. Thanks again for joining. We are now open for questions. What I would really like to iterate is CEINMS is a community endeavor, like I mentioned. So I really recommend people using the GitHub repo, the issues and the discussions to come up or to share your issues that you have while installation or other scenarios, but also try to come up with discussions and help each other out, so we can try to make it more than what we planned it out to be. Right, so now I'm looking for questions, and I thought I saw a hand from Sachin, but I don't know if you still have a question, Sachin.
Yeah, I have one technical question from Sartori. Like when you do lower limb, prosthetic model, so especially for either knee and ankle joint, the muscle characteristic and moment generating capacities changes significantly after amputation. So since CEINMS-RT relies on that OpenSIM-based musculoskeletal model, how accurately can represent that residual limb musculature and its altered biomechanics? So however, moreover, how is that missing segment of the musculoskeletal chain compensate for that torque estimation process to meaningful control for the prosthesis in real time? So that is being considered there.
Yeah, so in an amputation scenario, what we do is we measure the EMGs from the residual limb. These EMGs, they go into a musculoskeletal model of the missing limb, and this musculoskeletal model is scaled and calibrated to match the contralateral limb, which is intact. So that's how we do it at this time. And then the torque that we estimate from this model is actually driving a prosthesis, and the prosthetic angle, the kinematics of the prosthesis, is fed back to the model, to the CEINMS model, which then adjusts the kinematic dependent states in the model. So the motions of the prosthesis will actually make the CEINMS model move, and that motion will change the muscle tendon length and the moment arms. So that's how we do it at the moment. I don't know if it's clear.
Yeah, thanks.
Other questions?
There's, I think, a question from Simone, but you answered, Roger. There was a question from Simone Fanni about the installation giving an error.
Yeah, with the CMake list, I think.
Yeah.
Yeah, that's the typo that will be fixed in the 1.21 release. Yeah, it was just a pound sign that was missing. Yeah.
Okay.
Okay, there's another question from Hussein, who asks, would you recommend using EMG or IMU for better information? IMU is much easier for his use case.
Which one was it? Sorry, I was reading out.
The third comment from the last, Hussein Lekesis.
Yeah.
His question was to use whether to use EMG or IMU.
Would you recommend EMGs or IMUs for better implementation? IMUs easier to use for my studies. Well, the thing is that so the current versions of CEINMS real-time requires so if you want to estimate active, so if you would run CEINMS real-time right now with IMUs only without EMGs, then CEINMS real-time would assume a zero activation in the muscles, and the simulation would only simulate passive forces. So as you flex and extend your joint, you will stretch and flex, and stretch and shorten your muscle tendon units. And CEINMS would only estimate the passive force in tendons, the passive force in muscles, and would give you the passive torque from that movement. If you add EMGs as an input, then you can also estimate the active state of these forces. So the active forces due to muscle contraction. So you need right now both EMGs and IMUs if you want to estimate the net torque, the net biological torque due to active and passive torques in a joint.
Okay, we're still open for more questions.
There's a question from Irene. Apologies, you replied already?
Yeah. The question was, what you use for dialysis? We need only the EMG. I don't know if this one has an IMU. Maybe it has, but we don't use that one. So
It's not so accurate.
It's not so,
yeah,
okay.
we prefer to use the.
So what Salvatore does is he uses the quaternions from each exon's IMU and then has his own algorithm that finds the joint.
There's a question, can I set up the trigonal light system? I think there's no difference in that sense.
Yeah, I think so. So what you have to do is you can use install only the SDK, or maybe you can install all the software. But what you need is the Trinio control utility software to establish a communication, the sensor and your PC. So it is no problem, you can do it.
Yeah. And also, I think what's worth saying is that Salvatore gave a demo with the dialysis system, but on the documentation, maybe one of you can go back on the documentation. There's a section where we have plugin templates, and these are available templates that you can use to develop your own plugin. So if you want to, but you have to share the screen because I don't see it yet. So if you want to,
yeah, I saw this.
Okay, so you're sharing it, yeah. So if you see at the bottom of this shared page, there's a plugin template, and there are three types of plugins. The first is called Sample EMG and Angle, and this is a plugin, is an empty plugin that is already gives you already a structure to essentially read information from an EMG sensor and from an angle sensor. So in that sense, you can use that template to establish a communication with any EMG system, not just a dialysis, but with any EMG system that can communicate on a UDP port, as well as with any angle sensor that can communicate on a UDP port. So yeah, if you have a dialysis system, you can use the available dialysis plugin that's already being implemented. But if you have another EMG system, you can start from that empty template and establish a communication with your own device. Then we have two additional plugins, templates. The second one is called Sample Angle Consumer. And this is a plugin that is an empty plugin that is meant for you to have a structure on how to communicate with an EMG device, with an angle device, and with a consumer. And the consumer would be a robotic device. It can be an exoskeleton or it can be a prosthesis that can consume torques given by CEINMS. So that is the plugin that you may want to use in that case. Right. There's another question. One follow-up on safety and physiological fidelity when CEINMS real-time is used as a high-level estimation without embedded low-level prosthesis controller. With safety architectures, do you recommend to ensure safety motor interaction? For example, do you use supervisory controllers, hard limits, or command torque velocities, impedance forces-based safety layers, latency-aware predictive filtering, or watchdog mechanisms, and how are these validated? Yes, absolutely. So CEINMS real-time is only providing a middle-level controller or a high-level controller, depends on how you interpret. So we do not provide any low-level controller. It only provides a way to decode mechanical forces from muscle, tendon units, and joints from EMGs and joint angles, right? But then when you feed these torques, these EMG-dependent torques to the low-level controller, you need to make sure that at the low-level controller you have safety measures implemented, and these safety measures, they typically should be hardware measures and software measures. So you want to have some hardware motor limits to make sure that the motor does not hit the end of the range of motion. But in our case, we also implement software limits. So for example, we have some virtual walls so that when the axle of the prosthesis reach those walls, they are actually reached with a very low velocity so that the motor does not hit with high velocity against the end stop, which would, in a repeated experiment involving several minutes or hours of walking, for example, with a prosthesis or with an axle, if the motor would hit the end stop with high velocities repeatedly, it would damage. So yes, you need to implement safety measures, but this is typically on your side, because CEINMS real-time is only acting as a middle-level controller, is only decoding torques to then be fed into a low-level controller.
And there's one more question from Feng. I don't know.
Yeah, the most applications in CEINMS are moving activities. How about its reliability in static activities like sitting? Is there any study test the validity of the CEINMS-RT joint loads or muscle forces? We did not. So the CEINMS developer communities, which again at the moment comprises University of Twente, McGill, and Griffith universities, we have not done systematic tests on static type of activities. But what I recommend, what we always do when we calibrate our models, is that we always include a static trial. So, for example, if you calibrate a leg model, we not only do we use locomotion data for calibration, but we also use static standing trials, because that allows the model to understand what are the passive parameters in the muscles to be tuned. So it's very beneficial to really include a trial where somebody is standing statically, or we never included sitting trials, but static trials, standing static trial, yes. And that helps the calibration. It really helps tuning the passive force length relationships in the muscle. So that's very important. But we do not have a published study that systematically assess how good we are at tracking sitting torques, static sitting torque or static standing torques. That we don't have.
I see a question from Felix. Do you want to switch on your audio?
Yes, thank you. I was wondering, as this workshop is also happening as part of the SWAG project, when you are implementing the CEINMS-RT system into an assistive or therapeutic device, what are like main bottlenecks and challenges you had to overcome to implement the system in a setting with a therapeutic or clinical or just an assistive device.
Yeah, I think that the most important thing is to make sure. So before you use, so CEINMS real time is, it's not a toolbox that you press the button and it gives you the answer. You have to be critical yourself. And the first thing to do is to make sure that before you use CEINMS real time for the real time control of the device, you need to make sure that your model is valid, which means that you need to assess how well the calibration step worked. And that is the most important, that's the single most important aspect. So you need to calibrate your model, and then you need to assess how good the model is. So you need to run the calibrated model on additional data that was not used for the calibration, maybe involving slightly different walking conditions or arm reaching arrangements. And you need to be sure that the model predicts reasonable torques in those scenarios. After you have assessed that, then you're ready to go to the real-time control part, and you're ready to use that model to control a device. But before you do that, you need to make sure that your model has learned to predict reliable torques that make sense from a mechanical perspective. So you need to be a little bit critical yourself in assessing the output of the model. That's, in my opinion, the most important part.
Thanks, Massimo.
Right. Thank you.
Thanks for the question, Felix. If there are no questions, I'm also curious from the people joining today, how many of you are using CEINMS and what kind of applications are you working with? I mean, you can feel free to switch on your mic or put it in the chat, because we're also very curious, how are people using it in the end? Go ahead.
But I didn't use CEINMS. I use OpenSIM. But for EMG based controller and all, I'm trying to use now. So that work I'm doing currently.
Okay. Is there a goal that you want to use CEINMS for? Is there a robotic device that you're trying to integrate with, or
yeah, it's a robotic prosthetic control, robotic prosthetic ankle I have made, so that I want to control that. Yeah.
Okay. Thanks. Anybody else wants to share?
There's also questions on the chat. Building on your point about low-level safety control, do you see potential for learning-based or adaptive safety layers that can co-train with CEINMS real-time in a prosthesis? For instance, using reinforcement learning or residual policy adaptation to correct unsafe transition from. Yeah, absolutely. I mean, basically the sky is the limit, right? Because essentially CEINMS provides a model-based approach to estimate torques from EMGs. The advantage with respect to a neural network is that a neural network would be an end-to-end type of estimator. So it would map EMGs and joint angles into torque, but it would not show you the intermediate steps. It would not show you tendon forces, tendon strains, moment arms, fiber kinematics, fiber velocity, muscle forces. With CEINMS, you have everything. But now that you have that model, you can essentially, combine it with machine learning or AI models to to somehow combine the best of both worlds, right? And there, the sky really is the limit. So you can indeed combine AI techniques with CEINMS and make sure that the output torque of CEINMS, they are safe, for example, and they comply with safety limits. So that's totally possible. And and I think we will see many applications in the future of this.
Oh, thanks.
I think we have a follow-up on the question about static activities. I think Rajnish is asking if it can predict torque for isometric tasks.
Yes. Static activity mentioning. Yes. So yeah, absolutely. The literature of CEINMS actually started really with estimations of forces and torques in isometric conditions, and then we progressively transition towards dynamic tasks. But yes, we are totally, the CEINMS real time is totally capable of predicting torque in isometric conditions. We have several studies where we use dynamometry at the ankle joint to estimate static torques at the ankle joint. There are also studies at the knee. So it's totally possible to estimate isometric forces in isometric conditions. Yes, I can also point you to this to these studies. I can maybe leave some of the studies on the chat. Yeah.
Cool. Right. So I think we've answered most of the questions in the chat. Just maybe another open call for if anyone else wants to share something about their use of CEINMS, feel free to do it. Go ahead, Hussein.
Hi, thank you for the presentation. We are trying to develop a lower limb exoskeleton for the people with knee arthritis, and we are trying to make their knee open, basically, during walking. And I am just trying to think, like, what would be the benefit of getting a muscle force feedback? Because what we are trying to do is basically the making the knee in proper position. Do you know what I mean? So, and I am thinking to use your software in this case as a feedback mechanism.
Yeah. Well, if the application is OA, in the end, what you want is really to understand what are the compressive loads acting on the knee, because the position of the knee alone will not assure you that the compressive loads and shear forces will be below dangerous limits, right? Because it really depends on the co-activations of the muscle. We know that when you want to estimate the compressive loads, which trigger OA, 50% of these loads, they're just contributed by muscles during walking. So I think what you would want to do in reality is to estimate in real time the compressive loads using CEINMS, and then to provide exoskeleton assistance when the loads go above a specific dangerous level. If you would just use, yeah.
So I tried to make the instantaneous center of zero velocity path line optimized to control the system. But yeah, maybe as you're saying, checking the compressive force would be another source that it is aligned properly. But because I am using 4-bar mechanism, I don't know how I can use that information to align the mechanism again, but I'm not sure. But it is definitely a useful tool. I will try to use it and let's see how it goes. Thank you very much.
Yeah. If you have questions, let us know. Yeah.
Thank you.
You have a question, Sachin, or?
Yeah. Hi, Sartori. One small, like not question, but about the EMG, we primarily capture that surface level muscle activity. So its control bandwidth and depth resolution are limited, especially in amputees. So do you see any potential to integrating with sonography with CEINMS-RT to access more deeper muscles and improving that torque estimation? During prosthetic control and all? Like, so are you trying to use that SMG as well?
Yeah, so there are a few aspects here. So EMGs you're right, EMG signals can only be measured from superficial muscles. And deeper muscles, they are not recordable with surface electrodes on the skin. So there are a few things that you can do. So you are suggesting the use of ultrasonography, and that's a possibility. And we also have some projects running with the combined use of ultrasonography in EMGs. But there are a few things that we also developed in the past that are a little bit simpler and more viable. On one hand, we developed a synergy-based approach where muscles are not controlled independently by the nervous system, but they are controlled in group of synergistic muscles. And so it's possible to use EMG factorization techniques such as PCA or non-negative matrix factorization to understand the structure of this synergy. And if you know the structure of the synergy, then if you measure a few EMGs with your electrodes, you can infer the activity of the other muscles by employing the synergy. With Irfan and a student from our team, we published this year a method on IEEE transactions on medical robotics and bionics that is called the inverse synergy approach that does exactly that. So if you have a few EMGs, you can invert the synergy matrix to essentially reconstruct the activity of the other muscle. So that allows you to somehow, with a smaller set of EMGs, to detect the activity of the others. That's one approach. Another method that we developed in the past is called hybrid modeling, which uses simultaneously EMG and static optimization in real time. It's available in the offline version of CEINMS, not yet in the CEINMS real time. But with that approach, you use your EMGs to drive the muscles for which you have EMGs. And then you use static optimization to estimate the activity of the remaining muscles. And so you have the activity of all the muscles. So these are two techniques that may be a little bit more viable than combining ultrasonography. However, if you had ultrasonography, that is certainly a very viable way of using it. And I see, that's really where we want to go also with CEINMS. We want to extend it potentially to drive not only the models with EMGs, but also with other type of sensors. So right now we're using EMGs and joint angles, but in the future we can extend the platform to also, accept ultrasonography data, which can certainly be used. So, and if the community is willing to do that, also, yeah, feel free to also apply and make these modifications and share them back on the Git. But that's also something that we are interested in doing, and I think sooner or later we will make this approach as well.
Thanks.
Cool. Then I think we can take a few last questions, or we can close if there are no more questions. I will just summarize the environment and then close today's session. Any last questions? Okay, all right. Then what I'm going to do is once again show you the GitHub environments, because that's sort of our landing page. Right, so this is just a reminder that this is our main sort of where things are. So on the GitHub project, CEINMS real time, we have the 3 repo spins. At this point in time, if you want to install CEINMS, the easiest way is to clone this repo. So don't download it, clone this repo, and then it installs all the dependencies and CEINMS for you. It also accesses this repo. So it does that automatically, and that's how we do it right now. And for questions, so for issues and other discussions, we refer you to the issues page on the core CEINMS real-time, the core project or the core repo, and also discussions over there. And if you want more background information, feel free to take a look at that, read the docs. If you feel like there's some information that's missing and you would like us to add it, or if you would like to also contribute, feel free to let us know, and we can make this more sort of informative. So also we are open to suggestions from that side if you want.
The repository of the read docs is also public, so people can contribute.
Yeah. So this is indeed all of them are open source, and the repositories that you see here are open source, but we also have a few private repositories. So once they are ready to be public, for instance, the plugin of Salvatore with the Extens UDP, then we also make that public. So we keep making this larger. Thank you so much for joining. I think it was really nice to hear from all of you, and also the nice interactions and also nice questions. And also thank you, I think, Massimo, Salvatore, and Roger for setting this up. Anything else we need to add before we can close for today?
No, thank you. Yeah, we will, as Irfan said, we will provide a recording of the sessions on our YouTube channel. Thank you for being here, and if you have questions, additional questions, that you know how to reach us. So let us know.
Bye everyone.
Bye.
Bye.
Bye, everybody.